Good afternoon. Welcome to this week's colloquium of PRL. In fact, today we have a terrific speaker, uh, Professor Dipankar Banerjee, Director of ARIS, Nainital. To introduce the speaker formally and to conduct the proceedings, I will now request Professor Nandita Srivastava, Deputy Head at the Solar Observatory of PRL, so to please do the honors. Nandita, over to you.
Thank you, Professor Pallam Raju. Good afternoon, everyone, and welcome, Professor Dipankar Banerjee and my friends. It's a matter of great pleasure for me to introduce a good friend and colleague, Professor Dipankar Banerjee, today. Professor Banerjee is an astrophysicist. He received his bachelor's degree in physics from St. Xavier's College, Kolkata, and a master's degree in theoretical physics from the University of Kolkata. Then he went on to do his PhD from the Indian Institute of Astrophysics, Bangalore, and then did two postdoctoral assignments in reputed institutions in Europe, one at Armagh Observatory in UK, another in the Catholic University of Leuven in Belgium. As you are all aware, Professor Banerjee's research interest is in the physics of the sun and in the solar atmosphere. He has done a lot of work involving theoretical and numerical modeling using solar data, both from the ground as well as from space-based instruments. And these works have been recognized internationally as they have made a big impact, a significant impact on our understanding of the sun and space weather. Professor Banerjee is the co-chair of the science working group of the ISRO's solar mission, that is Aditya. He is also the project coordinator for the National Large Solar Telescope Project, NLST, that is a 2-meter ground-based telescope which is planned to be installed at a Himalayan site and will be observing the sun. He is also involved with NASA's Punch mission. Professor Banerjee has more than 120 peer-reviewed publications with around 3,000 citations in international journals, and he's also an honorary fellow of the Indian Academy of Sciences. I feel his enthusiasm and passion for science is very infectious. This is evident as he is currently supervising 6 PhD students, while 11 of his students have already completed their PhD. He's currently serving as the director of ARIS, Aryabhatta Research Institute of Observational Sciences at Nainital. As some of you are already aware that Dipankar is a good communicator and motivator, not only in the field of science, but also as a part of Bengali theatre group Smaranik. He is regularly performing in plays in national and international theatre festivals and encouraging young people to participate. He's also trained in Hindustani vocal. Today, if I remember correctly, he's delivering a PRL colloquium after almost 11 years. That is one solar cycle. The last colloquium he gave was in 2009. I think he talked about waves in solar corona. So today, without much ado, I would like to invite Dipankar to give his talk on colloquium on long-term study of the sun using the Kodaikanal Digitized archive. Thank you. Over to you, Dipankar.
Thank you very much, Nandita, for a generous, introduction. I hope I can do a justice to this colloquium today. I'm just trying to share my screen, and I hope you're able to see my slides now. Can you please just confirm on that? Oh, so
yes, but not until now
it's back.
Now
okay. Yes. So yes. It's a pleasure for me to give this colloquium. Though in a virtual platform, I normally prefer to have a face-to-face interaction and really see how much I am able to communicate. But with these difficult times, we try our best to use this platform. Nonetheless, I hope it allows a lot of people to come closer at these difficult times. So my title today is the long-term study of the sun using Kodaikanal Digitized archive. So before I get into the digitized archive and its resources, I will talk about a little bit of our sun, and particularly an object called sunspots. So it's going to be a more of a story of sunspots to start with, and I will come back to this diagram or this animation, which is our new result from one of my student work. Before I get into my work, I would also like to tell you where I am from. At this point, this is the two campuses of Aryabhatta Institute, or ARIES. At Nainital, we are here at the top of this Manora Peak. This was earlier called the UP State Observatory, and in 2004, it was taken over by DST, and it became ARIES. More recently, we have a new campus, which is 50 kilometers east of Nainital city, called Devasthal, and it is indeed a place where you can do prayer for the devtas. And our tool for that particular purpose is the best telescopes what you can have. And currently, we are hosting the India's largest nighttime telescope from that particular site. This is a close-up view of the Manora Peak campus. My office is somewhere here in this building. So we have a combination of old telescopes and the accommodations of the faculty, the staff, and the students. It's a vibrant place. We do have a mini auditorium and guest houses. So it's a small little campus, but a pretty beautiful campus. And you see in the background the plains, which is about 2 kilometers down below. And then this is the nation's pride now, the 3.6 meter Devasthal optical telescope. And this telescope is a national facility. And anybody, and I'm sure there are a lot of users from PRL as well for this telescope. Incidentally, I got an email from my namesake, another Dipankar Banerjee from PRL, yesterday afternoon or early evening for a special observing possibility, and we could manage to give him about an hour and a half at 11 o'clock in the night. So I hope he could get his NOVA in a special mode, and the data has been already transferred to him. So we are trying to make it most modern facility in the country, and work as a collaborative way across the institute. So please look at the science opportunities and submit your proposals. It's a completely open policy for the data in terms of the standard science methodologies. Okay, so now I get into this today's story about sunspot. So sunspots are dark, spots seen on the surface of the sun, and they are always associated with regions of strong magnetic field. Highly concentrated magnetic fields are there in the sunspots, and they were discovered by Hale more than a century back. And more modern, images gives a closer view of this. They always come in pair, and you see here them. And there are different structures of the sunspots and so on. I won't go into the detail of the high-resolution observations of the sun or the high-resolution observation of the sunspot. Today, I'm going to talk about more of a statistical properties of the sunspot, how they appear in the sun, and why they appear at certain time, small in number and large in other times. So this is called what is plotted here is sunspot number with last 400 years. And it was discovered by Swabe that this sunspot number seems to be varying with time. Of course, Swabe's observation was restricted to this period. He observed that at certain period, you have lots of sunspot, and in certain times, you have hardly any sunspots. So alternate peaks of solar activity called maxima, followed by quiet period called minima. And the time variation is predominantly cyclic, with a mean periodicity is about 11 years. As you can see from these 400 years of sunspot record, that there has been period where this solar cycle have been much more active than the other one. For example, this in the last century, in the 1950s, there was this cycle which was the strongest for many centuries now, it appears. Whereas again, there were a period between 1650 to 1700, there were hardly any sunspots recorded. This was discovered by Maunder, and that's why it is called Maunder minima. And still, we do not understand completely what really happened in that time. Is it that there were sunspots, but they were not observable with the possible observing tools or the telescopes they had? Or it was really something to do with the sun, where sunspots were not being produced at all? So now, how the sunspots are produced and why there is a cyclic behavior, and again, some other properties of the sunspots appearing on the solar surface at certain latitude, and with the progress of the solar cycle, their movements and so on, that will be my discussion today. Let us now again come back to these sunspot observations and try to see that some more properties of these sunspot pairs. Now, what I show is on the background is the magnetic field measurements, which is available only in last, say, 40, 50 years. Before that, we did not have regular synoptic observations of the magnetic field. We only had images from, of course, white light or calcium K, which is a chromospheric feature, and H alpha. So I will be talking about mostly today about those. But what is to be noted here is these two magnetic field concentrations have an angle between them. So this is called a tilt. And that tilt, increases with latitude, because I'm seeing you a closer view of this sunspot pair. If I look at this overall solar disk image, I will see that this tilt angle between the two opposite polarity sunspots, here you could see there is a white patch and that there is a black patch. So these are the opposite polarities representing the two concentrations of the magnetic poles. And this is a global view, as I just indicated, that if I take a full disk image and look at the magnetic map, the magnetic field concentrations, I see the picture like this. Here, of course, the two polarities are indicated by green and yellow, with a very strong fields as blue, that the core of this sunspot. So a sunspot pair is also commonly known as active region. Often, when there is such an active region, it's just not one pair of sunspots. There could be, many pairs of sunspots, and there could be possible magnetic connectivity, which is also of varied in nature. Those observations we only understand, or sort of we could see regularly from more modern observations. So active regions have systematic tilt, which increases with latitude. The polarity orientation is opposite to the two hemispheres. This statement means if I now look at the northern hemisphere, and if I look at that the yellow patch is to the right side of the blue patch here, right? So the polarity orientation is having certain sense. Whereas if I go to the southern hemisphere, that pattern is completely opposite. So here the green patch is on the right side of the yellow patch. And this is called the hemispheric polarity rule. And that also changes every 11 years. So 11-year cycle has to explain a lot of other properties as well. And those are the things which I would point one by one. And the current understanding also about the sun's magnetic field, as we understand from the magnetic field measurements and different modelings and so on and so forth, I will try to give you this insight. So here, this movie actually is showing you this magnetic map for several decades, whenever our synoptic observations of the magnetic field has started. So here it is actually showing you almost 30 years of magnetic field observation. So here you see there is a period over which the sunspots, there are a pair of sunspots, they appear in certain latitude. But when we move to the solar cycle, you see the sunspot number is again more increasing. So we are actually reaching towards solar maxima. But here what has happened is that these sunspot pair, they seem to be more migrating towards the equator. The strong fields are migrating towards the equator. And then around 95, 96, you will see that we are approaching. Oops, sorry, I have to go back. So around 95, 96, we will see that this is again around a minima. So here hardly any sunspots. This is again, it happened 11 years before 95. So it's about 1886, 87. Again, there was a minima period. And then again, sunspots start appearing. They start appearing in a higher latitude. But then with the progression of the solar cycle, they appear to be more to the closer to the equator. And then there are hardly any sunspots. And again, the ascending cycle of the sunspot, and this polarity also reverses and so on. So this is the overall property of the magnetic field which appears in the two band. What we understand now is that these sunspots, of course, come from interior. Inside the sun, there is a convection zone, and most likely at the base of the convection zone, there is a dynamo which is operating, and some magnetic flux concentrations, they are in the form of flux tubes, and when they are rising, they are driven by the convective flows and also by the differential rotation of the sun. I didn't talk about so far about the rotation of the sun. Sun rotates around its own axis, but sun doesn't rotate as a uniform body. It rotates differentially. That means equator rotates faster than the pole. This makes life completely different as compared to a standard solid body rotation. So this is a property. If I now stretch that particular animation which I was showing in the previous slide into this kind of plot, this is called the butterfly diagram. What it shows, again, the property, as I said, that there is a equatorward migration of active region. Then there is another thing to be noted here. There is a poleward migration of the decayed diffuse field. From that animation, you won't be able to see that very strongly, because this field, after the sunspot pair leaves for certain days and so on, then the active part moves to the equator, whereas the diffuse field, they migrate towards the pole. So this is called a polar rush. Somehow, this particular thing, what you see here, is going towards the polar direction. And also to be noted here, the stronger field have one polarity, which is this blue guys. This is the majority polarity, which is going towards the equator, whereas this diffuse field has a yellow or the opposite polarity. Now, there is another interesting thing has happened. Sun has a magnetic polarity also globally. So northern hemisphere sometimes will have a north polarity, magnetic polarity, whereas the southern hemisphere will have southern polarity. But now, with every 11 years, this polarity also reverses. Here, you see that effect here. This yellow polarity component of the magnetic field will now interact with these blue ones, and then there will be a cancellation, and then dominantly it will be yellow. So earlier 11 years almost, this was blue, the northern hemisphere. This becomes yellow in the next 11 years. So this is called polarity reversal. So this is again another very important aspect of the solar cycle behavior, which has to be explained by any theory which you invoke. So these are some of the properties. So now let me sort of give a very brief schematic representation of the dynamo as we understand. As I indicated, the sun has a poloidal field in the r theta plane, and then somehow from this poloidal field, the north-south directed field has to be responsible for the generation of the toroidal field in the form of a sunspot. And this toroidal field in a cyclic wave should be somehow producing back this poloidal field. So this is the principle of a dynamo. So here, this is the toroidal field, as I indicated, that these kind of flux concentration probably there at the base of the convection zone. This is called the tachocline, and they are there initially. And because of the rotation, rather the differential rotation of this field, this poloidal field, which is normally is expected to be oriented north-south, it gets rotated and swapped, and then that is responsible for the generation of the toroidal field or the sunspots. Now, these toroidal field which has generated, as I indicated, has opposite polarity. So the plus ones are going towards the equator and the negative ones are going towards the pole. Now, in the pole, predominantly it was the plus signs. If you compare with my earlier animation where these blue and yellow representations were there, so slowly these these negative polarity will eat up these plus guys, and then after 11 years you have a polarity reversal as well. So poloidal field, because of the differential rotation, it is giving you a toroidal field, and the toroidal field is responsible for the generation of the sunspots, but then decay of these tilted active regions of the sunspots along with this poleward migration is feeding back these polarity field, then will be dragged into the base of the convection zone. There is another conveyor belt which is actually rotating inside the convection zone. It is called a meridional circulation that takes away these polar field to the base of the convection zone, and then that becomes the seed field for the next solar cycle. So this is a cyclic process, as I indicated, that this meridional flow, and how you characterize this meridional flow crucially dictates that the time scales of these polar rush, and then effectively this polar field to be dragged to the base of the convection zone is completely dependent by the models what you invoke for this meridional flow. Whether you have such a one cellular structure, whether these flow patterns are like this, what is the kind of speeds of these meridional flow, all these are very, very crucial for the entire dynamo and its time scale. And of course, how you characterize the turbulence inside the convection zone in terms of the turbulent diffusivity, what kind of parameters which you use, dictates again the different time scales, or also the strength of the next cycle and so on. So this is the theoretical demand of all these different parameters. But then observationally, can we provide these observational measurements and parameters for the modelers? So that's a task which I am into, and this is a sort of again a summary of what kind of data a modeler needs. So for the poloidal field to the toroidal field and then back to the poloidal field for this cycle, what we need is two kinds of magnetic field measurements. One is for, say, as long as possible. This is called the sunspot so the sunspot area provides us an estimate about the toroidal field strength and the components and so on. Whereas we do not have really direct observations of polar field measurements for almost last 80 years or so. Even if you just talk about the last century, we do not have systematic observations of poloidal field at all. So we have to look at proxies or other ways of getting an estimate about the polar field. So this polar field, because as I mentioned, the polar field becomes the seed field for the next cycle, that dictates the timing and the strength of the next cycle. If you want to do a cycle prediction and so on, this is a very, very important parameter. And we are all, looking for that poloidal field measurements. And if measurement doesn't exist, is there an indirect way you can talk about the poloidal field? So I've been, focusing last 6-7 years primarily on this subject. So this is again a good example of the model, which is led by Andres and Dibendu from ISER Kolkata, and that's a sort of overall story which I was telling you so far. Been modeled into this kind of flux transport solar dynamo models, which can explain the sunspot number, which can explain the certain amplitude of the sunspot and the timing and so on. But again, as I indicated, that all these parameters, if you play around with, will change your strength and the timings drastically. So we have to observationally constrain these parameters for the modeler to be, able to predict the cycle much better. For this purpose, I have been using the Kodaikanal archive. This is a unique archive. This is probably one of the best in the world, I would put it that way. Of course, this was originally, been maintained by the Britishers before our independence. The quality of observations in the first half of the last century was actually amazing from this particular place. And we continued that, for last 50, 70 years as well with the same instrument. In fact, incidentally, a lot of people joke that how is that your observational data is so consistent and so uniform. So I normally comment now, because we never had money to change anything. So we just continued observing and use the same instrument. That actually makes a very unique data set, because you have not changed your filter, you have not changed your optics. So you have always observed, apart from the weather conditions which has deteriorated last 30 years. I will talk about it briefly. But the instrumental effects are not there in terms of the of course there is some small deterioration in the instrument, but fortunately these were very unique optics and so on, which has maintained its quality for century. So the other uniqueness of this particular archive is, from the same location every day there have been multi-wavelength observation. This is something which I also emphasize in last several years, that no other site in the world is so consistent in terms of having a regular observations in white light, calcium, and H alpha. So from this is an example at 1st January 1958. If you go back to the archive, you will see a white light image. You will see a H alpha and the calcium. We also have a unique data set which is called a prominence data set. Basically, the solar disk is blocked, and then if you have a feature in the chromospheric emissions in the form of calcium, then you can identify these prominences. So this is a very, very unique data for last 100 years, where these prominences are, these locations of the prominences, and then related with the space weather. It's a unique data source, and not many people have worked on that. We have recently done quite a bit of work, and the Westerners are very much interested to work on this prominence data. There have been a lot of challenges in handling this kind of data, and we have modernized this particular approach. So the point is that from 1904 onwards, almost, we have consistent data in these different wavelengths. All these data has been digitized, and they're open for the global community. We have produced several papers, and I'm very proud that most of these papers are led by my PhD students. And now the entire world is having full access to the data, and shared not only the raw data, but different levels of calibrated data. And you can download this data from this website as well. I will talk about the archive component, which has been also now maintained with IUCA in collaboration. So this is the telescope, which is, as I said, unchanged for more than 100 years. And still one guy goes up there in the morning if we have X-ray plates, because we are continuing this observation with the same traditional photography. Earlier it was photographic plates, then it was films, and now we have managed to get some films, and one particular image of the sun is taken almost every day. Still it is continuing. So this is also the building where some of you probably have given lectures in the auditorium, and the digitized lab is behind this building here. So that's the digitization lab. I will not get into full details of the digitization process and how we have generated these images and all that. But if somebody is interested, I can answer them at the end, or privately as well. I will be happy to do it. There are a lot of technicalities and challenges and so on. So essentially, from the raw image to the final image, there are lots of processes which one has to follow so that you preserve the information which is there in the original plates. We identify the sunspots. Again, I would also emphasize about one particular element from this entire thing, that I have been again fortunate to get very bright students, but I have always asked them for challenging tasks in terms of automation. I've done everything not on manual mode. In the past, the earlier generation, they had probably the patience and the time to do things manually. I don't do anything manually. I let the computer do everything. But there has to be consistency. You have to have sophisticated algorithms to do that. So that takes quite a bit of time to develop those. But once you develop, you produce a much more uniform data set. To me, I have compared with a lot of manual databases, and actually we are discovering there is always a human bias in doing things manually. And often what happens is, whatever procedures you follow, my eye, my sort of judgment will pick up one object as sunspot, and the next person will pick up something else. So that human bias also, have to be avoided somehow. So that's why I think the computer algorithms, if they're systematic, if they can address all the problems, of course, they do pick up artifacts as well. So you have to now find out ways to eliminate those artifacts. Again, that will be done with a consistent way, not with any bias. And if you do that, then you generate a output which is, to me, much more reliable, and so on and so forth. I don't use any human bias for any selection criteria at all. But algorithms are there to make that selection. It is not that you do not need a selection. You do need a selection, but that has to be done with a very systematic and a logical approach. So we have identified all these sunspots, as you can see, over several 90,000 plates, and then we generate this kind of sunspot area cycle. I will also indicate that somehow I prefer looking at sunspot area rather than sunspot number, because to me, the sunspot area is a better proxy for the magnetic flux, because at the end of the day, what we are interested is the magnetic content and the variations with time. So that way, the sunspot identification and their area, because the bigger sunspot behave differently than the smaller ones, and you have more errors in terms of detecting the smaller sunspots as well. I will not get into that details today. We have lots of publications in that context, how the bigger sunspot behave differently from the smaller ones. Are they generated by the same global dynamo, or there is some local dynamo? So there are a lot of theoretical work what can do on that. So we have produced this from the Kodaikanal data alone. We have produced this, and of course Greenwich data is the sort of is the calibration comparison what people normally use. So the correlation seems to be also quite good. And as I indicated, that we are looking at sunspot area, and I was particularly interested to look at the bigger guys against the smaller guys. So here there is a butterfly diagram where you could see that the sunspot appears in the higher latitude with the beginning of the cycle, and then they progress to the lower latitude. The bigger one seems to be only appearing during the solar maxima. Here you could see this, what is plotted, over-plotted rather, is the sunspot area cycle. From the top panel also you see the same thing. So here this gives a very indication. So the red ones are the biggest area size sunspot, whereas the blue ones are the smallest ones. So what it appears that the blue ones are often appearing to the to the higher latitudes as well, whereas the biggest ones are always close to the much closer to the equator or in the low latitude, and they follow the solar cycle very, very strongly, and progressively that distribution is there. So this is again a sort of newer way of looking at the butterfly diagram as compared to the earlier thing. I would say that our group we strongly advocated to look at these particular aspects. And this is a more composite, more recent, as I showed in my first slide, the animation, which is produced by my former student, Sudeep, is now a postdoc in Max Planck. Now he has, combined data from 11 different archives. And this is probably the daily cross-calibrated area series for more than 100 years. And I think everybody will be using this particular area series now on. It's just not Kodaikanal alone. There are 11 data, sources across the globe, which has been cross-calibrated, and this is appeared in very recently. He moved to Max Planck, so this work I have been also participating, but with the combination of the Germans and others as well. Not everything is symmetric on the sun. So the northern hemisphere and the southern hemisphere do not behave identically in terms of their strength and their phase differences and so on. I will not have again, too much time in giving the details. But what is shown here, if I just plot the sunspot area in the northern hemisphere by, say, this red line, and the green by representing the southern hemisphere, you see that there is a difference between their peak amplitude when it appears. So there is a phase difference between the sunspot area peaking in one hemisphere as compared to the other hemisphere. So this is called north-south asymmetry, and this hemispheric asymmetry has a lot of implication in terms of the dynamo parameters. I would also like to tell you one thing, that as long as I was just working with the data, I was not so much excited about things, but I've started working with the modelers and different dynamo modelers as well. So there is a group in Russia, they have different kind of models, and then of course in India we have a very sophisticated model called Surya, which is developed initially by Arnav Raichandri, and now I work with his former students like Vidya Karak and so on, and we look at a lot of these properties from the observational side and the dynamo modeling side as well. So this is the beauty of this. This is a long list, and this particular slide will be available. So if people are interested, as I indicated, that there are different properties of the white light or the sunspot data alone. There is something called Waldemar effect. Then there is something called active longitude. Why sunspots appear at certain longitudes and not all? I only talked about latitude bands, but I didn't talk about longitudes. So there are certain features that why they appear in certain active longitudes. So we have a paper on that. Then, as I indicated, that sunspot sizes have certain implications. Then there is another feature called double peak of the solar cycle. We worked separately on that. In terms of the sunspot, there is a core which is called the umbra, and then there is a outer layer which is called the penumbra. So there is a ratio between the umbra and penumbra as well. So we have done work on that. Then, as I indicated, that the long-term hemispheric asymmetry has a lot of implication in terms of explaining the dynamo. Then more recently, my current PhD student is also did some work on the solar differential rotation for the last 100 years. Because as I indicated, the differential rotation is a very important parameter for the solar cycle. Why the sunspot cycle is very different from one cycle to another. The differential rotation parameters, are they different? We do not have internal dynamical observations for last 100 years. We have helioseismology results for last few cycles. Helioseismology has given us the first direct sort of estimates about the internal rotations. But before the advent of the helioseismology, we didn't have precise measurements of the differential rotation. There are, of course, earlier results using sunspot as a proxy as well. So now after this digitized form of the Kodaikanal data, now we have looked at the variation of this rotation as well from Kodaikanal data alone. So far, I was talking about only the white light data, which looks at the photosphere or the surface of the sun. Now I go little high in the atmosphere, namely the chromosphere, and we use this particular calcium line traditionally to probe the chromosphere, and these has been recorded in the terms of a spectroheliogram. These are slit experiments, and then you scan the slit to produce this disk image. So they are different than the standard white light images, which is taken from a just standard telescope. So these arrangements are very different, but this is again a unique data source. The data availability, as you see, there are typically several images per day, and then the image quality and the number drops beyond 1980. This is what I was mentioning, that the weather is a huge factor in Kodaikanal, and as you know, people have moved out of Kodaikanal because of a deterioration in the seeing and so on from the Kodaikanal. What we have done is, of course, we have digitized them, we have calibrated them, we have these this kind of calibrated different sources. But what is sort of very important in the context of the dynamo and understanding the full physics of the solar cycle is these Carrington maps. So this is one full rotation of the sun, and you produce, if you could compare with this Carrington map and the earlier image of the magnetogram maps which I have seen, they can be compared. Because now we understand wherever there is this brightness, what you see in the calcium, that directly corresponds to locations where there have been magnetic field concentrations underneath. So calcium provides you a direct proxy for the magnetic field location. Of course, there is very challenging if you really want to get a measure of the magnetic field. Even from the white light, we do not have a measure of the magnetic field. We only have the location where the magnetic field concentrations are. Here also, there are certain ways you can do it. We are doing it right now. If your calibration is up to the mark, then you can do certain calibration between the magnetic field and the calcium intensity for the period over which you have the magnetic information. So after the advent of regular magnetogram observations, say from mid-70s onwards, we have a good amount of magnetic data and calcium data. So you use that to calibrate or make a scaling and then go back into the history and try to get a magnetic map. So this is something which we have done very recently. I will talk about it. Of course, these are the locations where the magnetic concentrations are. They're called plages. So as I indicated, we do a lot of algorithms and thresholding. There are Otsu's method. There are other methods which we apply to identify these features, and then we can produce this butterfly diagram as well. We, for the first time, probably did a 3D rendering of the butterfly diagram as recorded from the calcium. So now you see, normally people use butterfly diagram only from white light data, but now we are doing it for calcium. And we see the similar feature. Again, I will not be able to go to this large volume of publications which has come from this. We have generated the Carrington maps. Then we have produced these confirmation that the plages are very well correlated with the sunspots. We have also looked at the different granulation and supergranulation patterns, what you see on the surface of the sun. This indicates that underneath there is a convection in the sun, and these supergranular parameters, whether they vary with the solar cycle and so on, we have done a detailed work on that. As I indicated, effectively, this is all directly related to the solar luminosity. Why people are interested in this is to look at the solar irradiance variation. So this is again some work we have done. We have also indicated that this 11-year cycle seems to be just not 11 years. There seems to be some memory of the previous cycle and the current cycle. So there is a possibility of an overlap of the two consecutive cycle, which is a new idea, which is called the extended solar cycle. And a lot of people in the US are now actually bombarding on this particular concept now. And there are new models which are coming to explain the extended solar cycle as well. And then, as I indicated, it is important now to have this sort of cross calibration of different calcium data sources from different observatories. This is something again I'm doing with another Greek and a German guy, and this is the first paper in that series. There are other work also in progress. I would also like to indicate that SOOT, one of the payloads on Aditya L1, is having a calcium channel. Apart from other chromospheric channels or filters, it also has a calcium filter. So we are very much interested to continue with the SOOT, and since it's a L1 mission, we hope that it may be there for one cycle kind of. So we have a full comparison of one cycle from SOOT along with our ground-based observations on calcium from different sites, and including we are continuing our observations on calcium from Kodaikanal in a different setup now, not from this setup, but it will be able to compare. Then last section, I will now talk about the other object which we look at the chromosphere from H alpha. These are called filaments. So these are like clouds of plasma in the chromosphere which seems to be floating. And these historically, when these plasma is seen on the disk, they are called filament because they are observed in absorption. Whereas when these same cloud is seen off limb, they're termed as prominences. So why I put this picture is, it's just a question of nomenclature. It's the same object which is termed as filament when they are seen on disk, and they're called prominences when they're seen off limb. So you can imagine that if you have observations of on disk from H alpha and prominence observation from calcium as a disk block from Kodaikanal for last 100 years, how much resources you have in Kodaikanal. So this is something which I'm trying to highlight, and we would like to work on this. This is again some of these elements which I will talk about for next 10 minutes or so is the multi-wavelength feature, combining the calcium. which provides you the information where the magnetic field concentrations are. H alpha provides you information about actually the magnetic neutral line. Normally, the H alpha filaments are known to be along the magnetic field lines, neutral lines. So that means there is two opposite polarities on the either side of this particular filament. If you can somehow combine this information about the magnetic neutral line and opposite polarity flux concentrations from calcium, you don't have the polarity information yet, but you have this information. Is it possible to combine these two information and produce a magnetic map? This is something which we are doing. I've just published a letter paper. I will show you that. So let me just, before that, let me highlight that again, we have a huge data archive from H alpha, which has been completely digitized. And as you can see again, beyond 1980, we have certain reduction in the number of plates. This is the comparison of the K. So the Kodaikanal Solar Observatory is shown in the bottom panel here, the data archive length. Only one place which can compare with such a long series is the MEDO. And right now we are working with the MEDO. MEDO data is still not digitized. In fact, we had a IU symposium a few years back, and after we presented the KSO thing so nicely, MEDO did project that. I mean, they have been projecting for last more than a decade, apparently, to the funding agencies, but they were not getting any funding for the digitization program. But I was told last year they could manage to get the funding, and the IU symposium did help a lot. And new results which is coming from Kodaikanal is really allowing others to show that how much the older data can be, because we are able to produce high quality papers in the most impactful journals as well. So as I was again indicating, if you compare with National Solar Observatory, this is in Japan, this is Big Bear Solar Observatory, this is again in another Japan sources. Kodaikanal is quite unique, and one of the oldest as well. So this is, and you have hardly any data which is comparable. We can produce the butterfly diagram from H alpha also. As I said, the filaments does indicate the location where the magnetic field concentrations are somehow. And we can, detect the filaments by, again, a lot of automated methods. And then their properties in terms of their sizes, in the orientation, the tilt angle, a lot of physics can be extracted from that. And you can produce the butterfly diagram. As I indicated, again, combining calcium information. This is the H alpha Carrington map. This is the calcium. Of course, these are data gaps. So this is, again, another interesting aspect. If you combine data sets from different observatories, you will be able to fill up these data gaps. From one single site, you cannot do it. So we have picked up a period for calcium, H alpha, and magnetic Doppler imager. This is space-based magnetic field information. If you combine this information, you get, that the location of these filaments are nicely following the polarity inversion line and so on. So with this information, now we went one more step and we produced this magnetic map for last first half of the century, because in the later half there are certain magnetic data available, but for the first half of the century there were nothing. So from say 1915 to 1960, we have produced this magnetic map where you could see the equator with progressions. You see the polar rush. There are a lot more information. There are in between, actually, there are some odd rushes. This has a very serious implications in terms of the space weather. We have one or two other papers which are coming up with this. This is a very, very important element, that suddenly if you see a sunspot pair which doesn't have the standard rule of the polarity and so on, these are called rogue sunspots. What are the effects of that in the next cycle and so on? So we are able to now study, because we have produced this magnetic map. So this is the first magnetic map produced for the first half of the century, which has appeared in a letter paper a couple of months back. The last series I will be talking about is this prominences, and from the prominences we identify the prominences. The beauty of the prominence data is we can measure these poleward migrations much more precisely, because H alpha data, if you look at the polar side, there is always projection effects and there are difficulties. Even from the space-based data, we have the same problem. But the prominences, since they're out of a limb, so you can see it, at all latitudes and not affected much about the projection effects. And then we are only talking about the locations, not the sizes. Sizes will have some implications in terms of projection, but you can indicate these kind of poleward rush. And as you can see that the poleward rush, at the speed at which this rush is, they're also not same at different cycles, and they're not same in the two hemispheres as well. So this is a result from the Kodaikanal, but now we are combining data from Kodaikanal, Nedo, for the period of historical data, and Kanzilhoy. This is a current observation which is going on, and you can see and identify this polar rush very, very precisely. So this is a sort of work which we have done it from and published some months back. There is again another work with the Americans we are doing, but they are looking at Big Bear and Kodaikanal combined way, and we have a few Chinese postdocs, and they're doing things manually in the US even. I don't know how they manage, but they have produced similar things. This is just under a review, and we hope will be available there very soon. So the point I wanted to emphasize again in today's talk is the multi-wavelength aspect. So one of the unique aspects about the Kodaikanal data is that it has simultaneous measurements in 3 wavelength band. This basically translates into 3 different heights. So we have full coverage of the sun, sunspot in terms of the strong magnetic field locations, filaments, locations of the neutral lines, plages. Also gives you indication about the surrounding weak field. As I indicated, weak field has a lot of implications in terms of the dynamo and the poleward migrations and so on, and the prominences, incubator for CMAs. I know Gopal is very much interested in this particular prominence data, and we'll be working with him as well for historical, other data sources to be combined and so on. So determination of the strength of the magnetic coupling by following the rotation of different features across different wavelengths, and also morphological study of a single feature, for example, sunspot in different wavelength, reveal the evolution of the scenario for magnetic flux tubes in a more comprehensive way. And that's our requirement in terms of if you want to really compare with theoretical models and the dynamo calculation. So this is a comparison about the butterfly diagram, but here I just wanted to indicate that there are other features from butterfly diagram which is not there in sunspot, namely the poleward migration component and the weak field component from sunspot, because sunspots only are depicting you the strongest field concentrations only. So this is the database which we have developed in collaboration with Ayuka, with most modern Python framework. This was done under the NKN-driven initiative project 2 years back. 4 or 5 years back, actually, initially 2016, when I made the database, it was all based on Java. But as you know, Java is getting more outdated and so on. And then Ayuka contacted us. They wanted to have their new software completely tied with our 30, 60 terabytes of data for the last 100 years. And we were happy to get us this particular website. And if you are interested, please, request for the data, and you can download the data and so on from there. So this is my last slide. Of course, I must indicate that this digitization program started many, many years back under the leadership of Professor Jagdeep Singh, and it was supported very strongly by Professor Hassan. And after Professor Singh retired, this was handed over to me, and probably I was enabled to get it into more modernization into the program, and completed the digitization and all the different levels of calibrations and making the data available to the global community. So I can take probably a little pride on making the data available to the rest of the global community. So this is notoriously known as Dipu's gang. In this particular project, it's only Shudeep who was involved earlier, who is a postdoc now in Max Planck in Germany, and Shubhamoy, he's in Boulder, Colorado. He's doing a lot of artificial intelligence and so on now in Southwest Research Institute. So these two were only involved in the digitization program. I have a new cluster of people, and here only Vibhuti out of this gang. Vibhuti is continuing with the digitization program. Others work in different other areas. Shubhamoy was still there. Still last, this image was taken last June in Leh after this school. And this is the lot of people who are the past members as well, who had important contributions in the digitization process. So when I was handed over the program, the digitization was in full swing. There were a lot of manpower and so on. But and I completed the task and made the other data products available. So thank you for your attention.
Thank you, Dipankar, for a very impressive talk, highlighting the importance of ground-based observations on long-term basis to understand the behavior of the solar activity. And I think it is also very important to understand or appreciate this aspect in the current space-based era. So you have made a strong case for the same very emphatically. Thank you very much. And now I would, I think, like to check the questions. It's a comment from Professor Hariom Vats. He says, very interesting talk. And a question, could there be differential rotation in magnetic polarities, north and south polarity?
Well, I won't say differential rotation in the polarities, but the polarity reversal always do not happen at the same time. So that has serious implications. So of course, one thing is also not very, we are not very sure yet whether the solar different atmospheric heights also is coupled to the surface and rotates differentially. So this is a question which we are going to address with calcium and other data sources as well. There are certain indications that it does rotate differentially even in the higher heights, and I think Dr. Bhatt has worked on that area as well. So in that context, I think it is still not very confirmatory that particularly the coronal heights shows any differential rotation. But in terms of the polarity reversal, this is very well known that there is a phase delay between the between the north and the south polarity reversal. There could be a situation that both the poles, which is very, very unusual, but it does happen in the sun, both the poles have similar polarity. So there is a phase delay sometimes. Yeah.
Okay, thanks. The second question is from Jaydev Sharma. Sir, how can we estimate hemispheric asymmetry in rotation in convection zone? Is it possible?
Okay, so the convection zone rotational profiles are deduced from the helioseismology result. So helioseismology looks at the oscillations on the solar surface, and then it interprets it looks at different order vibrations of the P modes, and it interprets about the rotational profile internally. And there, in certain places, I am not an expert in that field, but I think there is not uniformity in the northern hemisphere and the southern hemisphere always in the last 2-3 cycles, whatever solar helioseismology data is there. There are marginal differences in the rotational profiles, but I do not know whether they have the precision enough to really make a big, confirmatory statement in that. And as far as most of the numerical work goes, they put the sun as a symmetric sphere in most of the occasions as well. They don't consider this difference in the two hemispheres.
Okay. The next question is by Dr. Dibendu Chakravarti. How does the hemispheric asymmetry, one of your works, connect with the dynamo parameters? Does it imply that the meridional flow also has a hemispherical asymmetry?
Yeah. So in terms of the historical data, we do not really have that much of precision to talk about internal rotational profile changes and all that. So it's only the sunspot area and the sizes and the distribution location wise we have data. So here I brought this slide back. So here what it shows is this the asymmetry you can parameterize by different way, n minus s by n plus s. This is the dotted line which is shown here, and then you can also calibrate in terms of by 1000. But we find that this is a better way of doing the north-south asymmetry parameter. It has an implication in terms of the if the dynamo models becomes sophisticated enough to talk about these phase delays between the two hemispheres, as I was trying to indicate, that this meridional circulation takes the 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 weaker field which is now in the pole in the minimum and drag to the base of the convection zone. So the parameters of these meridional circulation, we are now trying to link with the polar rush. I didn't actually mention too much, but we are working on that. Is there a possibility of the polar rush, what you see from the diffuse field, can have some link with the meridional circulation? There is a link. We have to just eliminate certain other parameters to be conclusive enough, and that may give us a certain clue. And if, as I indicated, those polar rush in the two hemispheres were different, and if the dynamo theory can incorporate these things, they will be able to reproduce the solar cycle better way. Most of the time, actually, the solar cycle dynamos do not even consider this two different hemispheres. But I must say that more modern dynamo modelers, even Vidya, does produce two different hemispheres differently, and he is able to actually reproduce some of these. Even the Kichetinov, who was a co-author in this paper, they also have a different dynamo model, and they could reproduce these importances. They have serious implications.
Yeah. There's another question by Hirdesh Kumar. What is the cause of hemispheric asymmetry?
So effectively, what you can see is that this somehow, what we understand is the diffuse magnetic field which goes to the pole, and the other component, the strong ones, goes to the equator. This drift rates doesn't seem to be same in the two hemispheres. So that will cause the asymmetry. But now that will have why they are different in two hemispheres has direct link. What Dibyendu actually asked has direct link with the underneath parameters, right? Namely the the conveyor belt, which is in the terms of the meridional circulation, or even the differential rotation in the two hemispheres. Can they be but we do not have such precision yet to talk about it, but obviously they are linked.
Okay, the next question is by Yogesh. Is there any effect of hemispheric asymmetry on solar wind parameters?
Yeah, I'm sure there will be. I'm sure there will be, because what happens is, at the end of the day, as you probably know, the solar wind is dictated by the global magnetic field structure. So we know that the solar wind is asymmetric, and we have a fast wind and the slow wind. The fast wind comes primarily from the polar region, and the slow wind comes primarily from the equatorial region. But this asymmetric distribution, in terms of the latitudinal distribution, is very different during the solar minima and the solar maxima. Okay, so if that is the case, we most of the time model it as a symmetric global field. But if you really want to do realistically, by using the magnetic field extrapolations, now there are certain MHD simulations where they take the of the surface flux transport dynamo inputs and feed that into the solar wind model. So if they do that, and if the surface flux transport dynamo is fed by, again, realistic observation, then that asymmetry is fed already into the solar wind models. So I would expect that it will show eventually, but I do not know how much they're able to produce it yet, because we have not gone into that kind of resolution and precision, I would say.
Okay, another question by Himani Parmar. Why sunspots appear at higher latitudes first and then near equator?
Okay. A good question. So it is directly linked with the when the flux tube is actually emerging, it is subjected to this differential rotation and convection. So, and also the strength of the field will dictate where it will appear. So the magnetic flux tubes, why do they come into the surface? There is a property called magnetic buoyancy. Basically, it's very similar to if you take a rubber tube and submerge it into water, the tube tries to float to the surface of the water. So here, if you take the convection zone as this kind of fluid, and the flux tube, the magnetic flux tube as a rubber tube, the rubber tube has to, the flux tube has to come to the surface. But while it is traveling to the surface, it is dragged by the differential rotation. So it's a combination of, there is something called the Coriolis force also, which will dictate at what latitude it will come. Since you asked the question, in fact, now we have a reasonable understanding about the strength of these magnetic flux concentration at the base of the convection zone, and there are limits to it. If those flux tubes would have been much stronger, then rather than appearing at 30-40 degree latitude, they would have appeared in 70-degree latitude. In fact, there are stars where there are sunspots or star spots, they appear to very high latitude. And now we know that those star spots have mega-Gauss, hundreds of mega-Gauss, field strength. So that means, because of the strength of the field, they pop up much faster. So the differential rotation is not able to pull them to certain latitude. So it's a combination of these rotation and the convection, which dictates that it will appear at certain latitude. But as I indicated, because of this underlying the other flow and so on, with the progress of the solar cycle, these sunspots appear to the lower latitude, and the weaker field goes to the pole, and so on.
Okay. And the next, there is a comment by Dr. Somkumar Sharma. He says, "Dear Professor Dipankar, very interesting and informative talk. Thank you." There's last question by Sandeepan Bodhakur. How do you define the sunspot area mathematically while making the plot?
Okay. Yeah, it's a good question. I have not talked about it. So typically, these areas, as you understand now, is in terms of number of pixels and so on. So we have to know what is the solar disk area and how many pixels are covered by this sunspot. So there is a unit called a millionth of a hemisphere. This is traditionally a unit which is used for sunspot area. So from the name itself, you can make out that how many millionth of the hemisphere is these accumulated pixels are representation of the sunspot area.
Okay. So I think this brings to the end of the thing. I have a question about the rogue sunspots. How crucial they are, and in what sense they can dictate the the dynamo, the next dynamo for the second cycle.
You ask the question. It turns out to be now it's a very important element. In fact, if I could go back to this slide, as I was indicating that these polarities are going towards the pole, which is normal because this is opposite polarity to the existing polarity there. But in between, sometimes you see a sort of polarity which is not usual, and these belongs to this rogue sunspot, and that will actually be also responsible for the double peak, which I did not talk about. In fact, double peak has been only reported during the maxima because it is more clearly visible, but that double peak behavior can happen any phase of the solar cycle. And I didn't show that plot because of shortage of time. So we have these are more current observations from magnetic field, more recent observation from ground-based magnetogram. Here you see again similar thing, right? This red stuff. Here you see this blue stuff, which is going, and that is causing the change in this kind of polar field changes, and that fluctuation is actually translated to the next cycle. So these next cycle, certain phases you have space weather phenomena in the terms of suddenly you have lots of flares and all that. So people are even trying to connect that unusual, this kind of space weather phenomena and not say maxima period because of this behavior. So this is a very interesting, very new subject area which we are working on.
Which is not necessarily these be very strong magnetic fields.
Need not be.
Yes.
Even if the opposite polarity makes a big difference.
Okay.
They're a more unstable kind of thing. Yeah.
Okay. So thanks. I don't think there are any more questions. So I hand it over to Professor Pallam Raju.
Thank you, Nandita. Thank you, Dipankar, for this wonderful talk. I have a question of my own. I was kind of a bit curious in understanding the polar rush, and does the rate of the movement has something to do with, is it solar cycle dependent, and does it have some kind of precursors, because we know that colloidal fields have something to say for the next solar cycle. Does it tell something about the predictability of the next solar cycle?
Yes, yes. So what we understand, it's a very good important question. What we understand is the polarity reversal is, and the next cycle strength is crucially dependent on the strength of the polar field. If the strength of the polar field is stronger than usual, then you expect to have a stronger cycle, the next one. And what I was trying to emphasize today is the timing of the cycle also has a big link about this polar rush, the rate at which this polarity buildup is happening. Because at the end of the day, the buildup process is important, and after that, the output, how much polar field is generated, is also important.
Okay. Yeah. And are there any plans, or are you already implementing AI and kind of inputs into this, or what is the status?
Yeah. So since you asked the question, so what we are doing now, I have a in fact a program, ICPS program from DST. This is multi thing from AI and ML. So we are also digitizing now the sun chart. Sun charts are the hand drawn locations of these different things: sunspots, splodges, prominences, the filaments. Meticulously, individually, observers every day has drawn that meticulously. And those are done in colored pencils. So right now I am digitizing them, and there is a paper we are submitting after tomorrow, just a proof of concept of we have digitized one cycle of the data, and we are able to now extract those prominences or say filaments. Now what I will do is, from the sun chart, I will compare with the digitized data, and then we'll see how good the sun charts were. Also, one other important thing about the AI applications of the sun charts are that there are plates which has gone bad, say for preservations and so on. So there are data gaps because of the non-availability of good quality plates. That the sun chart exists.
Okay.
So it will also allow you to do a fill up of the data gaps. So, and then there are sun charts in Meadow. In fact, as I indicated, Meadow has not been able to digitize the the entire data, but they have they have produced Carrington maps, hand-drawn Carrington maps. So we are working with Meadow hand-drawn. They have made it available to a global community. We are working with the globe, their Carrington maps. We are producing our Carrington maps and then cross-calibrating them.
Oh, wonderful. And I have just one more last question. In terms of the hemispheric asymmetries, how do they change from one solar cycle to another, and also does it have any bearing on the extent of the solar active regions?
It does. Well, not individual solar active regions per se, but it has an implication in terms of the the length of the solar cycle also. Because as I was indicating, it's in an average it is 11 years. Sometimes it is 12 years. Sometimes it could be less. Sometimes it could be all the way to 13 years. It crucially depends on the polarity reversal timing. So I was just indicating, there could be a situation where you have the polarity reversal has happened in one hemisphere, but it has not happened in the other hemisphere. So these are very, very peculiar times. So those will have very serious implications in the subsequent cycle as well.
Okay.
Yeah.
Wonderful.
You see, the dynamo is not a linear process, so it's a non-linearity. So it's not a very sinusoidal thing. So all these non-linearity makes the life, more interesting, to be honest.
Yes, very, very, very good. I think it was. It has been a fascinating talk and an excellent discussion that we had. And I think I would thank you on behalf of PRL and on behalf of all my colleagues and all the people who are witnessing this, being present in this Colloquium. I thank on behalf of all of them, and I thank all the viewers and also who have joined us through this medium. And it's always, it's my, pleasant, duty to tell about the next, colloquium. Also, we are coming closer to Earth from the Sun, and we have a colloquium on internal boards in the mesosphere, a manifestation of atmospheric gravity waves, which will be delivered by an alumni of PRL, Professor S. Gurubaran from Indian Institute of Geomagnetism. So I would invite the attention of all of you, and also request all of you to be please join us on the next Wednesday for the PRL Colloquium. Please remember, if it's a Wednesday, it will be a PRL Colloquium day. Thank you very much.
And thank you very much, Pallam Raju and Nandita, two of my good friends. And I enjoyed my talk. I hope it wasn't, too boring. I could excite some importance of the ground-based, data, and that too historical data, as Nandita pointed out. In the space era, but I think we need to continue ground-based observation and combine with the space, data as well.
That's right. Yeah, that's the need of the hour, and Kodaikanal, the data set spanning this 100 years really, is an important tool, as you also nicely brought out. Thank you very much.
My pleasure.
Thank you, Dipankar.